Bismillahirrahmanirrahim. Assalamu alaikum dear students. I'm Arif and I welcome you all to lecture number 29 on the subject of computer organization and assembly language programming. The title of today's session is Hello World in x86 64 assembly, in which we are going to write, assemble, link and execute our first x86 64 assembly program. Well, this slide shows today's agenda. We'll start with a quick overview of different microprocessors and their corresponding assembly languages. Then we will have a quick recap of x86 64 programming model. We will discuss the required toolchain and the programming environment that we will be using in this part of the course. Then we will learn to use the toolchain to execute our first x86 64 assembly program named first.nesum. And of course, finally, we are going to have a demo of all this on the Linux terminal. Okay, so let's start with microprocessors and assembly languages. Well, this slide shows a list of some important microprocessors like Motorola 68000, which is a 16 or maybe 32-bit architecture launched in 1979. ARM stands for Advanced RISC Machine, launched in 1981. MIPS stands for Microprocessor with Interlocked Pipeline Stages, launched in 1981. Intel architecture IA32 was launched in 86. SunSpark, that is Scalable Processor Architecture, was launched in 1987. Motorola PowerPC. By PowerPC I mean performance optimization with enhanced RISC performance computing, and this was launched in 1992. Digital Equipment Corporation Alpha. AMD Advanced Micro Devices introduced x86 64 in 2000, and Intel introduced IA64 in 2001. Dear students, later both AMD and Intel took over the ownership of x86 64 architecture. Well, all these microprocessors have their own instruction set architectures. And in this part of our course, we are going to study the ISA and assembly programming of x86 64 microprocessor. And later, if you want to switch on to the assembly of any one of these architectures, I hope it will be a piece of cake for you all. This slide shows the Intel CPU's history. And I think we have discussed this in detail in lecture number 26. So let's move ahead. Well, dear students, assembly is good because it teaches us the underlying details of our machine hardware as well as how the hardware components work. We can optimize our programs for speed and size. And assembly is good for writing device drivers, operating system kernel, compilers, and embedded softwares. And of course, assembly is a must if you want to do reverse engineering. And of course, some people say that assembly is bad because the portability is lost. Only a few programmers in the world know how to read and understand assembly code. And of course, assembly programs are difficult to debug. Well, dear students, assembly is an unstructured programming language. By unstructured, I mean that it provides only extremely basic programming control structures, such as basic expressions, reading and writing the memory, jump operators, and test. And do keep in mind that there are no procedure calls. And if you want to jump to some other location inside the code, the argument passing is done manually. I am sorry for this typo. There is no loop facility, and There is no scope for the variables and function. Everything is global. But even then, jumps, tests, and basic read-write operations are sufficient to implement any program. Okay, before I start with our first assembly program, let me have a quick recap of x86 64 register set and the programming model, which we discussed in detail in our previous lecture, I think lecture number 28. Well, there are 16 64-bit general purpose registers named as R0, R1, R2 and so on to R15. Dear students, to maintain backward compatibility of programs written for 8086, 8286 and 8386 processors, and to access the lower bits of these 64-bit registers, Intel has used a special naming convention. For these first four registers, R0, R1, R2 and R3, we can use the names RAX, RBX, RCX and RDX as well. If we talk about RAX register and want to access its lower bits, we can use this convention. To access the lowest 8 bits, use AL. For the next higher 8 bits, use AH. And to access the lower 16 bits, use AX. And to access the lowest 32 bits, use EAX. And of course, to access the entire register, 64 bits of the registers, use RAX. Dear students, it is important to note that when you use 32-bit registers like this EAX in 64-bit mode, the assembly instructions will zero out the upper 32 bits as shown over here. However, this does not happen when you use 8-bit and 16-bit registers. And I personally could not find out any good reason as to why Intel and AMD has done this. And similarly for the next four registers, R4, R5, R6 and R7, we can use the names RSI, RDI, RBP and RSP respectively. And if you want to access the lowest 8 bits, you can use the names SPL, BPL, SIL and DIL. For the lowest 16 bits, you can use SP, BP, SI and DI. And for the lowest 32 bits, you can use ESP, EBP, ESI and EDI. Okay, so these are the 8 registers, and for the rest 8 registers from R8, R9, R10 so on to R15, these are the new registers. If you want to access the 64 bits, use these names R8, R9 and so on. And if we talk about just this R8 register and want to access the lower bits, we can use this convention as shown over here. To access the lowest 8 bits of R8 register, use R8L. And to access the lower 16 bits, use R8W. And for accessing the lowest 32 bits of R8 register, use R8D. L for low, W for word and D for double. And once again, dear students, be watchful. When you use 32-bit registers in 64-bit mode, you will lose the contents of the upper 32-bit, as these will be zeroed out after the operation. Okay, so now we have a fair idea about these 16 64-bit general purpose registers. Let's talk about the SSE registers. Well, dear students, SIMD instruction set was introduced in Pentium 3 in 1999 that allowed a single instruction to be applied simultaneously to multiple packed data items using 128-bit registers. At that time in 1999, we used to have 128-bit registers, XMM0, XMM1, XMM2 and so on to XMM15. All these 16 registers were of 128 bytes. And these registers are used to store or pack 4 32-bit single precision floating point numbers or 2 64-bit double precision floating point numbers or 2 64-bit integers or 4 32-bit integers or 8 16-bit short integers or 16 8-bit bytes or maybe characters. And this is how SIMD instruction worked on these packed data items. Dear students, these days latest processors also support this SSE extension, streaming SIMD extension, that extended the size of these 128-bit register to 256 and even to 512 bytes. The 256 bits registers are named as YMM0, YMM1, YMM2, so on to YMM15. And 512 registers are named as 512-bit registers are named as ZMM0, ZMM1, ZMM2 and so on to ZMM15. These SSE media registers will come into play when we will talk about the SIMD instruction in the later part of the course, inshallah. Okay, so in the previous lecture, we also talked about the 32-bit E flags register, which is extended now to 64 bits and named as R flags. In literature, these flags are divided into three main categories: status flags, control flags, and system flags. This status flag include the carry flag, parity flag, auxiliary flag, zero flag, sign flag, and overflow flag. And these flags are set as a result of some arithmetic or logic operation by the CPU. The second category is the control flags, which change the behavior of processor on some instruction. For example, the direction flag falls in this category, which is used for moving or comparing strings. When DF is 0, the string operations takes left to right direction, and when DF is 1, the string operations take right to left direction. And this flag will come, of course, into play when we will talk about the string instructions, inshallah. Well, the third category is the system flags, which control system properties and are accessible by kernel only. There are many flags that fall in this category. I have mentioned only three over here: the interrupt enable flag, the trap flag, and the resume flag. You can talk. If you are interested in seeing the details of these flags, read this slide out, or you can refer to the previous session. Okay, so we are done with the R flag register now. We are done with the general purpose register and SSE registers, and now comes the turn of the segment registers. Excuse me. Well, dear students, in 64-bit mode, segmentation is generally disabled, creating a flat 64-bit linear address space. The x86 64 CPU treats the four segment registers CS, DS, SS, and ES as 0, creating a linear address that is equal in size to the effective address. The two new segment registers, FS and GS, are exceptions, as they can be used as additional base registers in linear address calculation. And after the segment register comes the turn of the famous instruction pointer register that was of 32-bit in 8386. Its new name is now RIP and is of course of 64 bits. And out of these 64 bits, only 48 bits are actually used. And finally, there are other registers that I have mentioned in the miscellaneous category. like the control registers, which are responsible for computing the processor operating mode, real, protected or long. Memory management registers, for example the global descriptor table register, local descriptor table register, and interrupt descriptor table register. They fall in this category. They are used in protected mode for memory management. Well, the debug registers, namely DR0 to DR7, can control and allow monitoring of the processor's debug operations. And there are some machine specific registers as well that are used to control and report on processor's performance. Well, our detailed discussion on these registers is beyond the scope of this course. And of course, here is the linear view of the main memory as discussed in the previous session. And I have told you before as well, to save transistors on chip, today's CPU use 40 bit instead of 64 bits. Thus, the physical memory is restricted to 2 raised power 40 bytes, 1 TB byte. And finally, this is the logical layout of a process address space. This is important for our today's session, so let me describe this on the next slide. Well, dear students, the logical layout of a process image is composed of 4 main sections: the code section, the data section, heap, and the stack. Well, this code section contains the machine instructions to be executed. These are the machine instructions inside the code section shown over here as well. And of course, this program counter or the instruction counter contains the address of the next instruction to be executed. Above the code section, we have the initialized and the uninitialized data section. Then we have the heap, and finally over here we have the stack. This SP stack pointer, now known as the RSP, this points to the top of the stack. And one more thing to note is that instead of 64-bit of logical address, the logical address is of 48 bits as shown over here, making the total logical address space of 256 TB, out of which 131 TB byte is used for the user space process, and the rest is for the operating system kernel, which is not shown over here. Okay, I think that is enough. Now is the time that we should talk about the toolchain and the programming environment in which we are going to do x86 64 assembly programming. Okay, so let me talk about the toolchain and the programming environment now. My dear students, the set of programming tools used to create a program is referred to as the toolchain. And in this part of the course, we intend learning x86 64 assembly, and the environment or toolchain involved in the process are, first of all, the processor. And I assume that we all have a machine with x86 64 CPU, at least a Core 2 Duo or a Core i3, i5 or i7 will serve the purpose. Then as far as the operating system is concerned, you can use any 64-bit Linux distribution. I will be using Kali Linux. Okay, then for writing the assembly code, for example, if you want to write the assembly code for the x86 64 processor and the file name is first.nesm, we need to have an editor for writing this code. But dear students, you can use a text editor or a code editor or an IDE. Well, an IDE is an integrated development environment, which is a self-contained package that allows you to write, assemble, execute, and debug your code in the same place. Some IDEs that you can use for x86 assembly are Microsoft Visual Studio, Eclipse, Xcode, and Sesame. Code editors are limited to writing code and do not go beyond this stage. IDEs as well as code editors, they both provide features like code completion, hints and custom folding of section of code. Some code editors that you can use for x86 assembly are Atom and Sublime, and I will be using the text editors. You can use gedit or Vim. Well, after we are done writing our assembly program in this source file, we need to assemble it. And we all know that an assembler is a program that takes as input a stream of assembly instructions and generates as output a stream of equivalent binary instructions. Well, my dear students, there are a variety of assemblers that you can use for x86-64 processor, like NASM, Net Void Assembler, which is an assembler and disassembler for x86 16-bit, 32-bit as well as 64-bit programs. And this NASM is available for all Unisys, Mac OS and Microsoft Windows operating systems. YASM is yet another assembler and is a full rewrite of NASM. This GNU assembler GAS or AS is the default backend of GCC. And finally, MASM is the Microsoft assembler available only for the Microsoft platform. We will be using NASM for this part of the course. Well, this is the command that we are going to use to generate the object file from this assembly file. I will talk about this process in detail on the Linux terminal soon. For the time being, remember, we have written the assembly code in some editor and then have generated the object code using the NASM assembler. Okay, dear students, once we have assembled the source code and generated the object file, the next task is to link. The linker we are going to use in this part of the course is LD, the GNU linker, which is the default backend of GCC as well. We can use GCC for linking purpose as well. Anyway, the output of this linker is the final executable, which is stored on the hard disk. And to read the contents of this object file as well as of this final executable, we can use the obj dump as and the readelf commands. And finally, the operating system loader is a program that reads this executable from hard disk and loads it in the computer memory. And this is the logical process image that I have shown over here again. Okay, last but not the least, we can debug the running process using a debugger. And some famous debuggers are GDB, Radar2, DDD, that is Data Display Debugger, strace. You can use Intel debugger, and of course in this part of the course we will be using GNU debugger GDB with PIDA plugin. Okay, I hope the toolchain and the programming environment conceptually is clear to you. So now is the time to assemble, link and execute a Hello World assembly program. So first of all, let's see the structure. Well, dear students, remember the entry point or the execution point of all assembly programs will be the label _start. It can be main as well if you are using GCC, but for the time being, just assume that the entry point will be a label _start. Every assembly program source file will have a code section as shown over here and an optional data section as well. In our first Hello World assembly program, this data section will contain a Hello World message, and this code section will contain assembly instructions to print this message on the screen. and of course some assembly instructions to exit the program gracefully. So here is the x86-64 assembly code file named first.nesum. You can observe the section .data. This is the data section that contains the message learning is fun with Arif, and this is the message which we need to display on the standard output. As well as you can see another value 54 over here, which is the exit status of the program. I just want that this program should exit with the value of 54. Over here in the code section, these five lines of code are used to display the message on standard output, and these three lines of code, they terminate the program with an exit value of 54. My dear students, for the time being, just ignore the details of the instructions used in this program and just concentrate as to how we can assemble, link, load and execute this program on our computer. Okay, well, to assemble this first.nesum file, you use the nesum assembler and give this command on the terminal line. This nesum is the command. -f is the option which tells you that which is the file format in which you want to generate the output file. So this -f elf64 instruct nesum to generate the object file in the file format elf64, executable and linkable format in 64-bit. And there are other output file format like elf32, cof, win32, win64 and bin. Okay, so first.nesum is the source file whose name is given over here, and this -o option tells the assembler nesum to generate the object file with the name of first.o. So after -o, whatever file name you give, the output file will be generated with the same name. So you can give any name. If you do not give this -o option, the default is normally the name of the file with .o extension. So first.o. Okay, so we have done with the assembling part, and the next task is the object file need to be linked with the standard C library to make an executable, and this ld is the command that we are going to use for linking. First.o is the file to be linked, and once again -o is the option using which I am giving my final executable a name, that is my.exe. So once this command is executed, this program will be linked and an output file will be generated with the name my.exe. And finally, we need to load this binary file in computer memory and execute it. For that, you just write down ./my.exe, and the output will of course be displayed on the screen. My dear students, one point you may have noticed over here is that the size of the machine instructions is not fixed. At places you may find it of 8-bit, and at places you may find it of 16 bits and so on. In case of our hack computer that we designed in the first half of this course, the machine instruction size was of fixed size, that is of 16 bits, since that was our RISC machine. x86-64 is a CISC machine, CISC, so that is the reason that you see instructions of various sizes. The size of this x86-64 instruction ranged from 1 byte to 15 bytes. Okay, enough of it. Okay, so now is the time to make it happen on our Linux terminal. Let us move to our Linux terminal, which in our case is the Kali Linux. Okay, so here is the terminal of our Kali Linux machine running inside the virtual box on my Mac laptop. And let me first of all see who am I. So I am Arif, and let me check out the details of my machine. I'm using Kali Linux. You can see over here. You can use Ubuntu or any other Debian based Linux, and the Linux kernel I'm using is 5.3.7. and let us see some information about the CPU of this machine. ls CPU. Okay, so this was the command that I gave. Note the architecture is x86 64. The CPU operating modes are 32-bit as well as 64-bit. This is a multi-byte load store machine, and the technique uses the little endian, that is least significant byte is stored or written at the lowest address. And the address sizes are also shown. You can see this particular CPU use 39 bits physical address and 48-bit virtual or logical address. This CPU has 4 cores. Okay, so working on 2.9 gigahertz. This is the model name, Core i7, and there are other information as well. Okay, so next task is to install the required toolchain. And to install the required toolchain, you need to give this command sudo apt-get install. We need to install GCC, we need to install GDB, and we need to install NESM, and you do install build essentials as well. Sorry for the typos. Okay. Okay, so it is more or less the latest versions. Let me show you the version of GCC. So it is 9.3. Let me show you the version of GDB as well. And it is 9.2. Let me show you the version of NESM. And the version of NESM is 2.15. And the version of the linker, and that is 2.34. My dear students, once you have installed all this, do go through the man pages of the GNU compiler, the NetWide assembler, the Linux linker. Okay. So once you are done with the installation of all these required tools, let me check out my present working directory. So I am inside the lecture course, lecture number 29, and this is the file which is there. I have already written to save time first.nesm. Let's see the contents. Okay, my dear students, I will of course do a scuba diving into the details of this assembly source file in the next session, inshallah. For the time being, just note that this program will display this line of code on the standard output, and then it will exit gracefully with this value of 54. This value of 54 will be passed to the parent of this program. Okay, so we don't go into the details of the source code, as we will do that in the next lecture, inshallah. Fine, let me assemble this. nesm-felf64, the file format, first.nesm, the source file name, -o, first.o. So this is the name of the the object file I want to create, and optionally you can give the command -g as well, that is used to add debugging symbol in the object file. Okay, so let me do ls now. You can see we have the file first.o over here. Let me link this first.o file using the Linux linker ld first.o, and let me name the final executable myexe, and of course you can see the myexe is there. Let me run myexe. Okay, learning is fun with Arif, and let me check the return value, and that is 54. Well, dear students, this 54 is the exit value which is returned by this program myexe to its parent, and this $? is the environment variable that stores the exit value of the recently terminated process. Okay, so I think that is enough. We have done the job. Okay, so dear students, once again, don't worry, we will do scuba diving into the assembly code of first.nesum in our next session, inshallah. So that is it for today's session. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. Wish you all the best, happy learning, and Allah Hafiz.